Hello everyone. In this video, we are going to talk about Chapter 12, Section 12-10. And we are going to learn about the translating frame of reference. We're going to use the translating frame of reference to analyze relative motion. Relative motion is the keyword here. First thing first, we're going to learn to define the relative position. Let's say I have particle A and particle B with respect to the fixed XYZ reference frame. Given that for your RA, we have a position vector RA. For particle B, we have a position vector RB. In order to find the position of B relative to A, we have RB/A will equal to RB minus RA. And keep in mind that this is vector subtraction, not the simple algebraic subtraction. Now, let's put some number in. If I have RB, location of RB is defined by 10I plus 2J, 10 on the horizontal direction, 2 on the vertical direction. And then also, if I define RA as 4I plus 5J, meaning 4 units on the horizontal I direction, and then 5 on the vertical J component, that will give me the RA. In order to find the relative position over here, I am coming from A pointing toward B, okay, always pointing toward to the first letter, okay, RB/A will equal to RB minus RA, okay, so over here, we are going to subtract the I component, 10I minus 4I gives me 6I, and we're also going to combine the J component together. That will be 2I minus 5I gives me negative 3. Sorry, 2J minus 5J, that gives me negative 3J. Relative position will be, keep in mind the notation, RB/A, and then that will be the first vector, RB minus RA. Okay, so be careful with the directions of it, which one minus which one. Similarly, we're going to talk about relative velocity. Velocity, if I have velocity to determine the relative velocity of B with respect to A, the time derivative of the relative position equation is taken as VB/A equals VB minus VA, or written in the other way, VB equals VA plus VB/A. And in these equations, VA and VB are called the absolute velocities, and VB/A is the relative velocity of B with respect to A. And we notice over here that if we're writing it backward, there will be a negative sign. So VB/A will equal to negative VA/B. And similarly, we're going to talk about relative acceleration. Relative acceleration is as if we were taking the time derivative, first derivative with respect to time of the relative velocity equation. Okay, so this vector relationship between the absolute and relative accelerations of particle A and B, these relatives, this derivatives tells me A acceleration B/A, relative acceleration of B with respect to A equals AB minus AA, or AB acceleration B equals acceleration AA plus acceleration A of B with respect to A. Okay, we are going to look at some examples together, but before we do that, let's do a quick review of laws of sines and cosines. In any triangle, if I have angles A, B, and C, and their opposite side will be the lowercase a, lowercase b, and the lowercase c. A lot of sine says A over sine A equals B over sine B equals C over sine C. The numerator, lowercase abc, represents the sides of this triangle. And then on the denominator, the uppercase, the ABC, the sine A, sine B, sine C, refers to the sine of each of these angle. And the other one says loss of cosine. Loss of cosine says a squared plus b squared, a squared equals b squared plus c squared minus 2bc cosine A. B squared equals a squared plus c squared minus 2ac cosine B. And then lastly, c squared equals a squared plus b squared minus 2ab cosine C. One thing I want to highlight here is that under the condition, let's say, for example, if this angle right here is 90 degree, if I have angle C is 90 degree down here, okay? So looking at our last equation right here, under the condition that C is 90 degree, that means cosine 90 is going to be equal to 0. cosine 90 equals 0, meaning this entire term equals to 0. So, other words, under the condition that if the angle C is 90 degree, C squared equals A squared plus B squared. That yields to our Pythagorean theorem. Pythagorean theorem says if you have a 90-degree right angle triangle and your hypotenuse square C squared will equals to the sum of the two other sides square, A squared plus B squared. Okay, example. So I have two airplanes coming to each other. VA is having a velocity of 650 kilometers per hour flying to the right. And then VB here is 800 kilometers coming down at a 60-degree angle. We're looking for the relative velocity of B with respect to A. So again, keep in mind that velocity, the 650 and the 800 that's given to us here is the magnitude of the velocity. Okay, we're going to, velocity are vectors. We're going to break them into the respective direction, horizontally, vertically, I component, J component. So since velocity A is going straight to the right, all of that 650 becomes the horizontal component. All the 650 are the horizontal component of the airplane. So that means it's going to be just 650. Okay, 650 to the right. All of them horizontal component. The B component is slightly different. We are coming down at a 60-degree angle. Okay, and it's coming down. Coming down means that if I break this velocity, this direction into the horizontal component and the vertical component, means that both the horizontal component and the vertical component will be negative because it's coming down at a third quadrant. Meaning when I break it, horizontal component to the left, vertical component going down, both of them becomes negative. So I have negative 800 cosine 60, negative 800 sine 60. That gives me, break down my VB. Now, to find the relative velocity of B with respect to A, velocity B slash A, that's going to be VB minus VA. We're putting them together, right? But we are putting the I component together. So I have VB minus VA. There's my I component of the VB. There's my I component of the VA. Put that together, you have negative 400 minus 650. That gives me minus 1050. And then the second one down here, negative 692.8. This is I component only for the VB. Notice that for your VA, there's no J component. Sorry, 692.8. I meant to say the J component. J component only. For your VB, there is no J component. That means when I put them together, this is negative 692.8. That is the only J component. Okay, so there you go. That's my relative velocity of B with respect to A. Now, in order to find the actual magnitude of this relative velocity of B with respect to A, we're going to use the Pythagorean theorem. This is, notice that it's not multiplied by 2, by the way. Should be a square here and another square here. We're taking the I component and the J component square, the I component square, the J component, and the square root. That gives me the relative velocity of B with respect to A. And then I can do a tangent inverse. This will be not minus 1 here. It should be to the negative 1 power. That's tangent inverse. Or in your calculator, you can also type in arctangent. Either way, that gives me what angle is this relative velocity of B with respect to A. We know the magnitude. We know the direction. In the graphical method, we're going to look at using the law of sine. The graphical method, so instead of breaking it into the horizontal component and vertical component, I know VA going to the right, I know VB coming down with a 60-degree angle. Relative velocity of B with respect to A is going to be start from the ending point of the velocity A and pointing towards the ending point of the velocity B. So there, this side of the triangle will be my VB slash A that we're looking for. Using the law of cosine, actually, VB slash A square equals 800 square. This side is going to be 800. So I have 800 square, and this side should be 650. So 650 square and minus 2AB cosine 120. It should be, I think there should be a 2 right here. Okay, that should give me, look, a lot of cosine. Look, it should be 2 BC cosine A. So in other words, the over here should be a 2. Okay, so I just highlighted 2 times 800 times 650 and then cosine 120. That will give me the overall magnitude of VB slash A. And then we'll plug that into using law of sine. That will give me what angle would that angle theta be? What angle would that VB slash A velocity of b with respect to a to b. Okay, so we know the magnitude using the graphical method. We know the magnitude in the direction. A graphical method together with laws of cosine and laws of sine. Next thing, we're gonna looking at two vehicles, car A and car B. Car A going straight up, meaning I will only have the J component going vertical, and then car B is going at an angle 30 degree. So we know the magnitude of VA equals 40 meters per second, magnitude of VB equals 30 meters per second, and then acceleration AA equals 4 meters per second square, and then AB equals negative 3 meters per second square. And then we're looking for the relative velocity of VB slash A, VB with respect to A, and then also the acceleration of AA with respect, AAB, or acceleration of B with respect to A. Okay, so now overall here, what we're looking for two relative motion, relative velocity of B with respect to A, also relative acceleration of B with respect to A. First, we're going to write down, break our vertical component, and horizontal component for both of the velocity. Velocity A, since it's going straight up, we have 40J. Velocity B is going at a 30-degree angle reference with the y-axis. So I'm using the sine 30, cosine 30 here. Now be careful with the sign. Since it's going to the left on the second quadrant, that means I have a positive value for the j, positive value on the y, and then horizontal component is going to be negative. That gives me negative 15i. Okay, so over here, we have VB slash A, velocity of B with respect to A, VB minus VA equals negative 15I plus 25.98J. Okay, so and then that's my VB, and then minus the value of VA, that's 40J. So I am combining the J component together, and since this is the only negative 15 is only the I component, so combining them together, that gives me the relative velocity of B with respect to A. Using the Pythagorean theorem, that will give me the magnitude of the relative velocity of B with respect to A, and then using the tangent inverse, that will give me the actual angle of this relative velocity of B with respect to A. Keep going. If we're looking for the acceleration, notice that in our problem, AA, acceleration of A, acceleration B are given to us. However, be careful. This one right here, we know AB. Hold on. We know AA. AA. Let's talk about AA first, since it's a little simpler because it's going straight up. There's only one direction. AA is 4J. Magnitude of that AA 4 meters per second square. This is on the purely on the vertical direction, purely the J component. Okay, so that means purely the J component. That means I have 4J. All of them of is 4J. Purely the 4J component. Okay, so AA is simple. AB is slightly more complicated. There is the normal component and the tangent component. We know that we have a negative 3 right here, right? We're using that negative 3, which is the tangent component. We're going to break that negative 3 into sine 30 on the I and then cosine 30 on the J. You have negative 3. Now be careful with the direction. Again, on the second quadrant, we have a negative sign on the X component and we have a positive sign on the Y component. Okay, now do not worry about that. This negative it's a different thing. This is given to us on our problem. Okay, don't assume that's already included for the direction. No. So we still need to look. We have another negative sign for the horizontal component and the positive sign for the vertical component. Keep going. So this is all we're looking at so far is the tangent component. And then also we have the normal component. Remember from our previous slide, normal component, acceleration normal component will be the velocity squared divided by the radius of curvature, the rho. Okay, we know that the radius of curvature is 200 meters. So we're going to take using that 200 meters, and we know the magnitude of the velocity is 30. VB is 30. We're going to take that magnitude of the velocity 30. Okay, 30 squared over 200. V squared over radius of curvature. That gives me the normal component of the acceleration. And then still again, this thing right here, be very careful with the sign. Okay, so I do believe that this thing over yeah, so 30 divided by 30 squared divided by 200, I have a cosine 30. And then there's also the 30 squared divided by 200, that gives me a sine 30. That gives me the I component and the J component of the of the what is it called? Um, Acceleration normal component. I do believe over here should be a positive because I have it's on the second quadrant, negative on the x value, positive on the y value. Now putting them together, acceleration of b with respect to ab minus, that will be ab minus aa. We are combining the acceleration, two of them together. This is a j component. There's a j component, right? I component only b's got ab's got the acceleration b has got an I component, so that's the I component. And then we're combining the j component, right? AB minus AA. This give me the j component of the acceleration of b with respect to a. Now using the Pythagorean theorem, again, that is not multiplied by 2, should be a square here. That's not multiplied by 2, that's a square. Using the Pythagorean theorem, I can get the magnitude of the acceleration of b with respect to a, and then using the tangent inverse to get the angle, magnitude and direction. Okay, that's all I want to show you in this video. Hope you find it helpful. Thank you for watching.